Hi everyone, welcome back to chemistry. In this video, we're going to continue talking about chapter 4 in our textbook, and we'll start with 4.3, the atom. So an atom is the smallest particle of an element that still retains the characteristics of that element. So if you look over on the right there, you've got some aluminum foil. If you were to zoom in really close in that aluminum foil, you'd eventually see these individual aluminum atoms. Okay, they're kind of like the building blocks of the element. So you would see not just a few atoms of aluminum, you'd see, trillions and trillions, because they're really tiny. So if you looked at like a piece of paper and you put that piece of paper on its side and you were trying to measure the width of that piece of paper in atoms, you would have millions of atoms. Just in that tiny width of that paper. So they're really small. The ancient Greeks actually came up with this idea of particles that they called atomos, and that's where we get the term atom from. Excuse me, sorry. But they said that if you kept dividing matter in half over and over again, you would eventually get to the tiniest particles that you can't divide any further, and those would be called atomos. That's what they called them. But we didn't have like a specific scientific theory about atoms until a scientist named John Dalton in 1808. And his atomic theory is still forms the basis of atomic theory today. We've made we've made some modifications and stuff since 1808 when when his theory came about, but the basic understanding, his basic atomic theory is still very useful today. So in his atomic theory, atoms are tiny particles of matter. Atoms of an element are similar to each other and different from other elements. So aluminum atoms are similar to other aluminum atoms, but they're different from something like oxygen atoms, for instance. He also said atoms of two or more different elements can combine to form compounds. We talked about compounds a little bit. So some examples are, water is a compound, CO2 is a compound, etc. And then he said that atoms are rearranged to form new combinations in a chemical reaction. So you might put in a certain compound, or you might start with a certain compound at the beginning of your reaction, and then, by the end of it, you have a different compound. But you still have the same atoms. And this is really important, so I'm putting a star next to it, because atoms are never created or destroyed during a chemical reaction. So the atoms that you start with are the atoms that you end with. They might be bonded to different things. They're in different combinations than when you first started, but they are still all there. Okay, they're not created or destroyed during that reaction. So this brings me to a couple side notes. So John Dalton's theory of his atomic theory kind of gave way to these laws that we have. So there's the law of conservation of mass, which says that there's no change in the total mass of the substances reacting in a chemical reaction. So what does that mean? So that means that the number of total grams that you start with, right, before the reaction is the same as the number of total grams that you get back after the reaction. You might have some kind of different substance at the end, right? Things might be bonded differently, but you still have the same number of total grams before and after. So if you were in lab and you were heating something up and some of the compound or chemical that you were heating up turned into a vapor, right? That vapor still exists, even if we don't have it kind of bottled up with our reaction still, or it's not in the original container. It's still in the atmosphere. It's still here. Maybe it wafted through your hood and got vented away, but it still exists, right? So what you start with is what you end with. Or you could even think of like, even if you're heating a substance in a beaker and some of that substance gets stuck to the beaker and you can't get it off, yeah, you lost some of that substance during your reaction, but it's still there. It's on the beaker. It hasn't gone anywhere. So that's the law of conservation of mass. I hope that makes sense. And then there's also the law of multiple proportions, which says that the masses of one element, which combine with a fixed mass of the second element, are in a ratio of small whole numbers. So again, what does that mean? So looking here a little closer, we're familiar with these two compounds, right? That's carbon monoxide and carbon dioxide. I talked about those a little bit. Quick note, remember that these, I actually don't know if I mentioned this, but these numbers that you see over under the element are, they're called subscripts, and they indicate how many of that atom you have. So in this example, we have 2 oxygen atoms bonding with 1 carbon atom. Okay, and the reason I know there's 1 there, even though it doesn't say, is because anytime you list the atom and you don't say how many of it you have, we assume that there's 1. So over here, how many carbon atoms do we have? Yeah, we just have 1, and here we have 1 oxygen. Okay, so let me get rid of that. So in this carbon monoxide here, we have 1 carbon bonded to 1 oxygen. So that's a 1-to-1 ratio of carbon atoms to oxygen atoms. In this one, we have 1 carbon bonded to 2 oxygens, right? So that's a 1-to-2 ratio of carbon atoms to oxygen atoms. And that's what we see. That's what we observe in nature, is that they're bonding in these small whole number ratios. Okay, what we don't see is that we don't see these fractional numbers. We don't see these decimals. So we aren't going to get a half of a carbon bonding with 3 oxygens, or 1 carbon bonding with 0.25 oxygens, right? We don't get those kind of decimal fractional numbers. They're bonding in small whole number ratios. Okay, so this, I'm going to put an X through because we don't see that. Okay, so this will help you with one of your homework problems. So I just wanted to talk about that real quick. Okay, so electrical charges in an atom. So atoms actually contain even smaller particles within them that are called subatomic particles. So, but I didn't lie to you when I said atoms are the smallest up here, when I said atoms are the smallest particle of an element. They are still the smallest particle of that element that actually maintains the properties of that element, right? So aluminum atoms are the smallest particle that give aluminum, the element, its unique characteristics. But each atom actually does contain these smaller particles. But if you had, but we have these in all atoms. So these are similar across all atoms. We have these 3 subatomic particles. So hopefully that makes sense. So atoms contain the following subatomic particles. They have protons, electrons, and neutrons. So protons have a positive charge, and specifically they have a positive 1 charge. They don't depict that 1 there, but it is there. Okay, so it's a charge of positive 1. Electrons have a negative charge, or more specifically a negative 1 charge. Again, it's not depicted here. We just show the plus and minus to assume that there's an imaginary 1 there. And then neutrons have no charge. They're neutral. They have no charge, okay? So the way that some people like to memorize this is they think of proton starts with a P, and protons have a plus charge or positive charge. Protons positive, right? And then there's electrons, which I don't have a fun way of remembering that, sorry. And then there's neutrons, which I remember like neutrons, neutral, neutrons, neutral, no charge. Okay, and you'll start to just remember these things. All right, so like charges repel and unlike charges attract, or you could also think of that as, you know, the common phrase opposites attract. So like if you've used a set of magnets before, and you've tried to push together two of the same charge or two of the same sides of the magnet, you'll feel that tension with the magnets because they're repelling each other. They don't want to be, two like charges don't want to be next to each other, right? They want to be as far apart as possible. That's just something that we observe in nature. And then two negative charges do the same thing, right? If you put two of the negative side together, they still repel because they're still like charges. But if you have two opposite charges, positives and negatives, then those magnets are really attracted to each other. And if they're strong magnets, they snap really fast. And they can actually hurt you. Like I've used some strong magnets before and caught my finger in between them, and it hurt really bad. Anyway, so those are some of the subatomic particles of an atom, and these are very important, okay? And we'll do a lot of work with this. All right, so jumping back to kind of the history of understanding more about the atom, J.J. Thomson was another scientist. He was an English physicist, and he conducted this experiment that we refer to as the cathode ray experiment. And so what he did was he shot these particles. I'm going to kind of show you down here. He shot these particles in this cathode ray tube is what it's called, or it's like a glass tube. And he had two charged electrodes that tube was connected to. So he had a positive side and a negative side. And we call the positive side the anode and the negative side the cathode. Sorry, I was thinking about, I was trying to remember a mnemonic that I had heard a while ago, but it's not relevant to our purposes. Anyways, so what he found was when he was shooting these rays of these particles, which we now know as electrons, they were attracted to this positive electrode. They were attracted to this side. So he said, well, why would these particles be attracted to the positive side? Well, they must be negatively charged, right? Because opposites attract. So that's how he determined that there were particles called electrons and that they were negatively charged. He also, in a separate experiment, determined that these electrons that he discovered have a much smaller mass, or that he learned more about, have a much smaller mass than the atom. So the atom is much more massive than these teeny tiny electrons. So he proposed this. Actually, I kind of want to show you guys this next because it's still about cathode rays. So the cathode ray television are actually, this is just a interesting side note, but I don't know if you ever had these larger TVs, bulkier TVs in the past, but like, look how bulky this is. This is a cathode ray television, and these were common. This is how televisions were made until we got the thinner LCD screens, right? So now TV screens are like this even. Yeah, maybe a little thicker than that. I guess it depends on how much money you're spending. But yeah, in the past, like when I was a kid, we had one that looked like this. And what these do is they shoot a beam of electrons that's bent by coils of copper, and that creates a magnetic field. And those electrons hit this phosphor, what is it also called? I wrote it down because I was interested. Phosphorescent screen, that's what I wanted to tell you. So they would hit this phosphorescent screen and display images on the screen. And eventually, like, a picture is formed from these red, blue, and green images on the screen. So really cool. Just a cool side note. And so J.J. Thomson also, after his experiment with the cathode ray tube, he started to think about, okay, what does the atom actually look like then? Because now I know that there are these electrons, and I'm wondering, like, what does the atom actually look like? And so he proposed that the atom looked like something called plum pudding, and this is what plum pudding was, or is. It's a food that was actually really popular when he was around. I actually don't know if it's popular today anymore in the UK, but it was when he was around. And it had these, he's proposed that the atom was like a plum pudding, where the negatively charged electrons were these little plums, and they were floating around in this like positive pudding here of protons. So these would be the protons. We now know that this is not correct. This is not what atoms are actually like, but it was a model that he came up with. So then there was another scientist, Ernest Rutherford, and he worked with Thomson to test Thomson's model. So what he did was he had a thin piece of gold foil, and he aimed this beam of particles, towards the gold foil this way, right? And actually, I kind of want to represent them as particles. So let's kind of make them look like little particles, right? So he sent those towards a thin gold foil. And what he found was that these particles that he sent at the gold foil, and they were positive particles, they actually were getting deflected, some of them. So they were bouncing back away from the gold foil. But what he had originally predicted was that they would go through the gold foil. Some of them did, but a lot less than he thought. So they weren't going in a straight path. And those were the ones that were actually coming close to the atomic nuclei. Was there anything else I wanted to say about that? Oh, yes. So the big conclusion was that there must be a small, dense, positively charged nucleus in the atom that's deflecting these positive particles. Because remember, like repels like, right? Or like particles are repelling each other. So if these positive particles are getting deflected off of this gold foil, he came to the conclusion that there must be some kind of positively charged nucleus that is causing that to happen when those particles come close to that center. Okay, so this brings us to the current model of the atom. So the structure of the atom, an atom consists of a nucleus, and that's located in the center of the atom. And that nucleus contains protons and neutrons. Okay, and it represents most of the mass of the atom. We'll get into more of the details in a little bit. And then electrons actually occupy a large empty space around the nucleus. Okay, so the mass of the atom. So in an atom, the protons and neutrons that make up almost all of the mass are packed into the tiny volume of the nucleus. Okay, so you have this atom which has this nucleus here with protons and neutrons in it. And those protons and neutrons, what we found, are responsible for most of the mass of the atom. So much of it that we actually kind of negate the mass of the electron because it's so much smaller than the mass of the protons and neutrons. And what was found was that we have this tiny nucleus, right, of these protons and neutrons, and the electrons are actually really far away from that nucleus. I've heard it described as the nucleus is like a grape size. It's not, but just to put things in perspective, because remember, atoms are really tiny. But the nucleus, if the nucleus was the size of a grape, the nearest electron would be a mile from that grape. So really, really, really far away. So the atom is mostly empty space. Really interesting. And the electrons are the ones that are surrounding the nucleus and creating that large volume of the atom because they're so far away from the nucleus. Okay, so because subatomic particles are so tiny, chemists actually developed this unit of mass that is called the atomic mass unit, or AMU. And 1 AMU has a mass equal to 1/12 of the mass of the carbon-12 atom. And this is kind of gibberish right now. That contains 6 protons and 6 neutrons. So 1 AMU is also referred to as 1 Dalton in biology. And electrons have such a small mass that they're not really usually included in the mass of an atom. So when we talk about the mass of an atom, we actually really are only talking about the protons and neutrons. And I thought there was a table. Yep, there it is. So to make more sense of this, here's a nice table here. So notice that the mass is listed in AMUs now because remember, it's such a tiny, tiny number that we would have to write 0.0000000000000 for a very long time to write out that mass. So that's why we use AMUs, or the unit of atomic mass units right here. Okay. So if you look here, we have the particle, the type of particle, right? We have the symbol for the particle. So protons are P or P plus, and that's just to show that they have a positive charge, right? Neutrons are N or NO. The O is, or the 0 is to show that they don't have a charge. And then electrons, we always write E minus, and that's just to show that they have that negative charge. So again, there's the charge, the electrical charge that these particles have. So +1 for protons, 0 for neutrons, and 1 negative for electrons. And then here's the mass. So this is kind of helpful, I think. So you'll notice that the mass of the proton and the neutron are actually pretty similar, right? They're really close in mass. But the mass of an electron is so much tinier than the mass of the other two. So that's why we kind of negate the mass of the electron, because it's so small that it doesn't really make a big difference. It's like if you were going to jump on the scale at the doctor's office and you maybe take off your shoes and your coat because those are kind of heavy, but you're not going to take off like your earrings and, you know, maybe like a watch or something like that, because the mass of that object is so much smaller than you that it's not really making a huge difference. Okay, or a noticeable difference. And then here's the location in the atom. So again, protons and neutrons live in the nucleus, and then the electrons are kind of orbiting around the nucleus in this really fast manner. Okay, so learning check. Which of the following subatomic particles fits each of the descriptions below? Pause the video, try it out. All right, so A, found outside the nucleus, protons, neutrons, or electrons? Electrons, right? The nucleus is made of protons and neutrons, and the electrons live outside of that, okay? And then B, have a positive charge. Remember, positive proton, positive proton. And then have mass but no charge. Remember, we said neutrons and protons contribute to the mass of an atom, and neutrons have no charge. So have mass but no charge. All right. I think this video's been somewhat longer, but I don't think we have that much to go for 4.4. So let's do 4.4 and then we'll do 4.5 in another video. All right, so atomic number and mass number. So all atoms of an element have the same number of protons and the same atomic number. Okay, all atoms of an element, a specific element, have the same number of protons and the same atomic number. We'll talk about what that means. So the atomic number is a whole number that is specific to each element. You could think of it as like a fingerprint for that element. If you have the atomic number 11, you have sodium. Okay? If you have the atomic number 1, you have hydrogen. Atomic number 2 is helium. Number 3 is lithium. Atomic number 4 is beryllium. Okay, so each atom or each element has a specific and unique atomic number. That's the same for all atoms of that element. So if you have one sodium atom, the atomic number for that sodium atom is 11, as is for another sodium atom. Okay? And that atomic number is also equal to the number of protons in an atom. So when you're looking at sodium, we actually know how many protons are in an atom of sodium, and that's 11. Okay, so if we have an atom of sodium, sorry, I should have mentioned that Na is sodium. Sorry, it's one of those weird ones that's not super intuitive. So anytime you have an atom of sodium, it has an atomic number 11, and this equals the number of protons in that atom. Okay? And then the atomic number always appears above the symbol of an element in the periodic table. So remember, this is the symbol that shows what element you have. So the atomic number is always above that. So if you look at your periodic table right now, you can see those atomic numbers listed above. Sometimes it'll be in the middle, sometimes it'll be off to the side over here. It's still the same thing. As long as it's above the element symbol, that's the atomic number. Okay? All right. So if I asked you to locate or to tell me what element the atomic number 15 was, what would you tell me? Atomic number 15 is phosphorus. Yeah, it's a fingerprint for the atom. Okay, it's a fingerprint for that element. If you have 15 as your atomic number, you are phosphorus. So the atomic number equals the number of protons, which we said. So the atomic number for hydrogen is 1. So every hydrogen atom has 1 proton. The atomic number of carbon is 6. So every carbon atom has 6 protons. The atomic number for copper, that's this one's copper, kind of one of those weird ones, is 29. So every copper atom has 29 protons. 29 protons. Okay. So the atomic number tells you how many protons you have. Okay, so this is just showing kind of like a picture of the atom. This is like, very simplified, right? But this is what the nucleus sort of looks like for carbon. Okay, and you'll notice we have 1, 2, 3, 4, 5, 6 protons, right? We have protons in red. And then the neutrons look like they're in white, and we have 1, 2, 3, 4, 5, 6 neutrons. And we'll talk about that in the future, about the number of neutrons, okay? But for now, think about how carbon has an atomic number 6. So how many protons must carbon have? Well, it has to have 6, okay? Same thing with lithium. We count the number of protons in its nucleus there. We have 3 protons. Okay. All right, so atoms are neutral. So atoms would like to be neutral. They when they're neutral, they're happy. So for neutral atoms, the net charge is 0. So that just means, remember, net charge means the total charge. Total charge. So remember, if protons are positive and electrons are negative, in order for that atom to be neutral, we need to have the same number of protons and the same number of electrons, because plus 2 minus 2 equals 0, right? Plus 1 minus 1 is just 0. So for a hydrogen atom, for example, hydrogen, which has 1 atomic or 1 proton, its atomic number is 1, right? That hydrogen has 1 proton. So because atoms are neutral, how many electrons does that hydrogen have to have? Yeah, it has to have 1 electron to balance out that 1 proton, right? And to have a total net charge of 0. Remember, there are still neutrons in there, but neutrons don't have a charge, so we don't have to worry about them when we're thinking about the charge, right? We're just concerned with protons and electrons. Okay, another example. Aluminum has 13 protons and 13 electrons. So the net overall charge is 0. So when you're looking at the periodic table and you're noticing the atomic number for any of these atoms, and you're saying, okay, if, for instance, lithium has 3 as its atomic number, that means it has 3 protons. you assume that it's neutral unless you're told otherwise. And in the future you will be, but right now when you're looking at the periodic table, an atom of lithium is assumed to be neutral. So if it has 3 protons, it must have 3 electrons, or else it wouldn't have a net 0 charge. All right, I hope that made sense. If it didn't, let me know. All right, so learning check. Use the periodic table to fill in the atomic number. The atomic number, the number of protons, and the number of electrons. Okay?